Mic? Okay. All right. Yeah, so this is work I'm currently doing at Babylon, and some of this is still work in progress, so we'll see. Okay, trustless Bitcoin vaults. So what's the goal? So there's, we know there is Bitcoin, but unfortunately most smart contracts, or all smart contracts and applications using cryptocurrencies are on other chains because you cannot build them on Bitcoin given its limited scripting capabilities and so on. Okay, so there's a lot of asset on the Bitcoin chain, $2.4 trillion worth of asset, but the applications are on different chains. So how can we use this Bitcoin on these applications on other chains and get back the Bitcoin when you want? So you don't sell your Bitcoin or you don't give it to someone else to keep custody for you, but you still want to use them in applications here. So the current state of affairs for doing this is you have to go through some trusted intermediaries, so maybe WBTC or Coinbase BTC, where you give your Bitcoin to someone, they issue some wrapped Bitcoin on another chain here, and then you can use that wrapped Bitcoin as a stand-in for Bitcoin in all these protocols. But the issue is all these go through trusted intermediaries here, and maybe that's a reason why it's like very small amount of Bitcoin, Bitcoin's total asset value is actually used in this manner. Now you might say, okay, another method of doing this is to try to build bridges, trustless bridges that don't require any trusted intermediaries. Unfortunately, that seems to be a very hard job to do, and recent efforts in building these bridges using BitVM and other technologies still end up requiring some kind of trust assumptions and some third parties that you need to trust to either for liveness to get back your Bitcoin or for safety that your Bitcoin is not stolen by someone else. And even multi-sig bridges, which were before that, of course, require trust assumption on a majority of a multi-sig committee. So okay, seems like all the solutions so far require some trust assumptions to bridge your Bitcoin from Bitcoin to other chains. So we think a little bit differently here, and we say, okay, bridging the Bitcoin from to another chain is just one way of doing it. It's a means to get your Bitcoin on the applications, but not necessarily the end goal, right? The end goal is you want to use Bitcoin's value in these applications, and can that be done without actually building a full general purpose bridge that takes Bitcoin and mints some sort of a wrapped Bitcoin here and so on, right? So what does this mean? Let's take an example. So let's look at application-specific Bitcoin vaults. What does this mean? So let's take an example. Maybe there is Bob who wants to be a borrower. Bob wants to deposit his Bitcoin into this vault, and Bob wants to borrow some, let's say, some stable coin on Ethereum from the lender, Larry. And this Bitcoin that Bob deposits will be used as collateral. So in the happy case, if Bob repays the loan and the price of Bitcoin is still doing pretty well, then Bob gets to redeem the collateral. Whereas if the price of the Bitcoin goes down before Bob repays his loan, then the lender gets to liquidate the collateral. Right? This is a standard collateralized lending scheme. And these kind of protocols can be built on the smart contract chains, but not on Bitcoin. And Bob has Bitcoin, right? So Bob owns Bitcoin. Maybe he's a miner, but he needs to borrow stablecoin to deal with his daily expenses. So how can he do this? How can he borrow money without actually losing custody of his own Bitcoin, right? And that's the sort of primitive, this vault that we want to build in such a way that it's again, trustless. So Bob doesn't have to trust Larry or any other third party for his safety or liveness. Okay, so that's the example, and we think about how to achieve this. So in some sense, there are two challenges in achieving this. One is, okay, so what we're building here is this vault in which there is some Bitcoin locked, and depending on some condition on the smart contract on another chain, you decide which party gets to redeem the Bitcoin, right? So if Bob repays the loan and the price oracle says that the price of Bitcoin is greater than a threshold, all of these are part of the state of a smart contract on Ethereum or some other chain. How do you prove this state on Bitcoin so that only the right person can withdraw Bitcoin from the vault? So that's challenge number one, and this is hard because things are. It's very hard to compute things on Bitcoin directly. So you need to figure out some ways of. That's the reason the smart contracts aren't there in the first place. So we have to figure out some ways to deal with that. And the second challenge I'll talk about is how to enforce these vault rules in order to make this protocol trustless, so that Bob doesn't have to. As long as this condition is satisfied, Bob can unilaterally redeem his Bitcoin without having to trust Larry or any other party. And similarly, the other way around. Larry doesn't have to trust Bob, and so on. Okay, so let's talk about this challenge number one, which is how to prove smart contract state on Bitcoin, or in general, how to prove some off-chain computation on Bitcoin. So maybe let's, this is not a new problem, how to prove computation on a blockchain. Ethereum has done this for rollups, right? So rollups are scaling solutions on Ethereum. The computation is done off-chain, but you want to prove that the computation is done correctly on Ethereum. And there are a variety of different tools that has been used to do this in the case of rollups on Ethereum. And so let's try to learn from those. So one idea is snark proofs. Succinct proofs of the computation. So let's say you have some large input and a large program. You compress it down to a small proof and a smaller program that verifies this proof, and run this verifier off-chain. Run the verifier on-chain. So the advantage is that the proof is smaller, the program is smaller. You can run this on-chain with less cost compared to computing the whole thing on the chain itself. And this is sort of the approach used in ZK rollups. Many of you know about it. If we try to do this on Bitcoin, it's simply infeasible, because even this snark verifier program, if you want to implement it on Bitcoin's scripting language, then it's a program of like 3 gigabyte size, just the program. And there's a block size limit of 4 megabytes, so it's not going to fit in Bitcoin. So this approach simply infeasible. Okay, so there are other approaches. There is an optimistic approach instead. So optimistic approach says, okay, let's accept the computation, whatever has been done off-chain, unless someone challenges it. And if challenged, then there's an efficient way to disprove it on-chain. So here what you do is you still have the large program. You divide it into smaller chunks. And if somebody challenges that the program was incorrectly executed, then the challenger can do a binary search or a bisection game to narrow down on a small part of the chunk that he can disprove on-chain. So if you want to prove that the whole program was wrong, it's enough to show that a certain part of the program was wrong. And that saves costs, because you don't have to run the whole program or the whole snark verifier, but instead just a small chunk of the program on-chain. Well, this was one of the ideas that came up in BitVM, the first version. There are still drawbacks which make this approach impractical. One is you have to implement these chunks of the program in Bitcoin script, and also committing to the whole input of this program on Bitcoin chain requires a blow up of about 56x for each bit of the input. And again, this ends up becoming too large compared to the block size and so on. So okay, there was ZK proofs, verifying ZK proofs directly on chain. There's optimistic proofs where, or fraud proofs where you disprove a small chunk of the program on chain. People have also figured out there is a best of both worlds approach, which was recently called naysayer proofs in the Ethereum world. You can think of this as best of both worlds in the sense you compress the program down to a snark, and then you run the same trick of disproving a small chunk, now of the snark verifier, not of the original program. The advantage being now you just have to implement this one program on Bitcoin script, and also that this program is much smaller. Its inputs are much smaller than the original program, and so maybe this helps. So okay, this got to at least being somewhat practical. There were different kinds of designs along the same idea for Bitcoin. BitVM version number 2 and BitVM version number X, like iPhone versions, there are different names. You will see more coming soon. And so it ends up being somewhat practical, but then it still comes with pretty high costs. So committing to the snark proof is about 1.4 megabytes, which fits into a block, but it costs $4,000 to post it on Bitcoin. And similarly, the chunks of these program, each of these, again, barely fits into the block, 4 megabytes, but costs $11,000 to post it on Bitcoin.
Where are you getting these prices from? Because it costs nothing as well. So
okay, this was, we actually posted these transactions on chain, ran an experiment. It was based on the transaction fees rate at that time. Yeah, it could cost much more if Bitcoin is congested. So this is sort of a practical case scenario.
So a small comment is that because these are so big, they call non-standard transactions. You have to pay extra to get them in.
unless you're a miner yourself.
Yeah,
Yes.
So
these actually cost more than sending it directly to the mempool, because these large transactions are not accepted by the mempool.
Just as a point in time, do you remember what was the average SAT per VB price?
Yeah, so the mempools charged 3 sats per VB, but then because these are non-standard, you have to go through some services like Slipstream or directly interact with miners, and they charge us 11 sats per VByte. That's the fee rate. Okay, so it still ends up costing about $15,000 to just verify this computation on Bitcoin in this manner. Okay, so then we tried these approaches from to try to learn from Ethereum, and then if these don't work, let's go back. Let's try to learn from Bitcoin instead. What does work on Bitcoin? There's something called hash time lock contracts, or HTLC. That is something that works on Bitcoin, and pretty much every application on Bitcoin, like Lightning networks, payment channels, whatever exists there, has been using hash time lock contracts. So what is a hash time lock contract? You can put in Bitcoin into a UTXO, which is just the terminology for a Bitcoin associated with a certain spending conditions. You can put your Bitcoin into a UTXO, which has 2 spending conditions. So either someone can reveal a particular secret. You have a commitment to the secret written into the UTXO, and if you open that commitment correctly, you get the Bitcoin. One guy can get the Bitcoin. So that's the hash lock. And then you have a time lock component. So if nobody reveals the secret within a certain timeout, then the Bitcoin has another path of going. So for example, it can be that if Alice reveals a secret, Alice gets the Bitcoin. Otherwise, after a timeout, Bob gets the Bitcoin, or something like that. So that's the concept of HTLC. So far, it's very limited, right? Like, you have to reveal a secret, and then you get Bitcoin. This doesn't talk about how to encode this off-chain computation, which we wanted to verify on Bitcoin. That was the challenge we want to solve, right? So how do I use HTLC to solve this? Well, it would be nice if we could design a scheme this way, right? So we got as far as encoding the whole program into a snark proof and having a snark verifier. And it would be great if we can do the following, that Bob, when he wants to withdraw the Bitcoin, he posts a proof of proofs that he repaid the loan, let's say. So that's the proof of the off-chain computation. And it would be nice if, in case Bob has an invalid proof, then the other party, the lender, Larry, can reveal a secret and block Bob's Bitcoin withdrawal. So that's sort of the challenge path. And if Larry doesn't challenge, then you can assume the proof is valid and Bob gets to withdraw the Bitcoin after timeout, right? So this is kind of trying to use the HTLC framework. But what we want to do is Larry should be able to reveal a secret to stop Bob from withdrawing, or if and only if the proof is invalid, the proof that Bob submits. So we want some box like this, where you put in a message M, which could be the snark proof. And this box outputs a secret S chosen by Bob if f of m is 0, so the proof was invalid. And it doesn't give you any information about the secret if f of m is 1. So that's the box we would like to design to use HTLC to solve this problem. So for some of the cryptographers in the audience, you might recognize that this kind of a box is called witness encryption. And this problem is known to be quite hard, and no practical solutions for that yet. But then what we note is that, we don't really need witness encryption here, because I make a slight change here. Let's say Bob signs the proof that he sends. So only Bob can generate this signature, signature on the proof. And now I modify the box so that the box takes the signature on the proof, Bob's signature, and then outputs the secret under the same conditions. And this is a variant of another problem called conditional disclosure of secret. So here it means that conditioned on f of m equals 0, you can reveal the secret. Otherwise, you cannot reveal the secret. And this problem is pretty solvable. It's practical. People have solved it. And the key insight is that Bob can encode the secret somehow in his signing key, so that when Bob reveals the signature on the right message, you can reveal his secret. But otherwise, if Bob signs, let's say, a message that is a valid proof, or if Bob doesn't sign any message, then you don't get anything about the secret. And how do we solve this conditional disclosure of secret problem? OK, maybe I'll give you a little more formal definition before that of what I mean here by this particular variant of CDS. So there is a setup function, which takes the function f, a setup algorithm, which takes the function f, in this case, the snark verifier. And Bob runs this setup. He outputs a signing key, a verification key, and a decryption key, and a secret S. And let's say Bob commits to all of these, and let me also implicitly assume that Larry can verify Bob ran the setup correctly. He can verify it off-chain. I don't want to get into that part right now. So let's say Bob ran the setup correctly. And now when Bob wishes to withdraw the Bitcoin, Bob will generate a signature. Using his signing key and the message, he'll generate a signature sigma. He provides that to Bitcoin. And Bitcoin will verify that the signature is correct according to the verification key. So let's try to use some signature algorithm that we can verify on Bitcoin. Turns out we can do it. And then once the signature is revealed, Larry can use the signature along with the decryption key to reveal the secret if the proof is invalid. Otherwise, you cannot get anything about the secret. So it turns out a solution to this comes through a cryptographic primitive called garbled circuits. I'll probably speed up through this a bit to avoid the detail. Basically, what garbled circuit does is it encodes the function f as a Boolean circuit using binary gates. And for each wire of this gate, it assigns two values, two randomly chosen values called labels. And it generates ciphertexts that allow you to basically find out the secret corresponding to the output here if you have the right signatures here. So for example, the secret key will be the random labels chosen here. And a signature will be, suppose your input is 0011, then your signature will be you choose A0, B0, C1, and D1. This is called a Lamport signature, by the way. And once you have these particular labels, you can evaluate the circuit and recover the secret corresponding to the output. So if it's an invalid proof, for example, then you will be able to decode I0. So the result is that this whole snark verifier can now be compressed down to a small secret. And what you need to post on chain is only the commitment to the snark proof and the small secret. And this brings the on-chain cost down from about $15,000 to $100. The data is, the total amount here is about 100 kilobytes, and it's not just the scaling based on the amount of storage, but as I said, it's also now standard transactions which charge much lower fee rate. Okay, there is a trade-off. So we move all the evaluation, all the computation and storage off-chain to do this. And so off-chain, someone needs to store the ciphertext generated in the garbled circuit, or in other words, this decryption key. And that is around 40 gigabytes. And it also takes some computation time to evaluate or to encrypt and decrypt these secrets. Okay, so putting all of this together, the kind of protocol you get is that Bob can log Bitcoin into his vault. Bob claims Bitcoin when, suppose Bob repaid the loan. He claims by posting a signed proof on Bitcoin. And then now either if the proof is invalid, Larry can stop him, or otherwise after a timeout, Bob gets the Bitcoin. And there is a similar path for Larry. In case the Bitcoin price falls and Larry wants to liquidate, then Larry posts a signed proof of the claim that Bitcoin price has fallen down, and an oracle has signed it, for example. And Bob can challenge it, otherwise Larry gets the Bitcoin after a timeout. And what are the security properties that it achieves? So there are three basic actions in this vault. So first action is Bob and Larry can create this vault. Second action is that Bob can withdraw collateral when he has repaid. And the third action is that Larry can liquidate the collateral when the price goes down. And the property we get is that all of these actions are trustless. So each party can, for example, Bob can withdraw without having to trust Larry, and there are no other parties in the protocol, and so on. Yeah, so with that, I conclude, and time for questions.
Okay, maybe you can start setting up as we have time maybe for one question.
Yes.
Whenever I see trustless, I get there is trust in Oracle, for example, at least for something.
Okay, there is trust in Price Oracle, which is fundamental to the lending application. So, yeah.
How does this extend to applications beyond lending? For example, like asset bridging?
Yeah, okay, so one of the, as I mentioned in the starting of the talk, one of the reasons why we can do this in a trustless manner is because the set of parties that can obtain the Bitcoin, here the lender and the borrower, it's a fixed set in advance. And that is what enables the trustlessness, whereas it turns out if you want to do a generic bridge where anyone can redeem the Bitcoin from their wrapped Bitcoin, then it turns out you need trust assumptions through to actually do it on Bitcoin. So we make it application specific, but yes, there can be other applications beyond lending. Maybe just to state one example, you can deposit Bitcoin and mint some stable coin using this as collateral. And again, you have this kind of withdraw and liquidate path to do that, and so on.
All right, let's thank Srivatsan again.
Thank you.
And the next